Welcome everyone to geometry. We want to take a look today at section 10, which is lines, rays, and segments. And what we want to do is we actually want to take a step back a little bit. We've talked about in the preceding sections 1 through 7. We developed some ideas. We had quite a bit of discussion on undefined terms. We talked about lines, points. We talked about polygons, of course, two-dimensional stuff, expanded into three-dimensional stuff, polyhedra, and that was awesome. That's good. But what we want to do is we want to kind of break things back down again. We want to go back to the building blocks. So in section 8, we talked about axiomatic systems. And what we're going to do is we're going to build everything up from the axioms, so that way we can learn what geometry is at its fundamental level. And to do that, for a lot of what we have, we want to write proofs, right? If we start off with a couple basic ideas, we get this new idea from those. So we start with a couple axioms, some undefined terms, we produce a new concept or idea, a new theorem, and we can prove that theorem using the axioms. We come up with a new theorem, and when we come up with this, our second theorem, then we say, all right, we tie that back to, we prove it with the previous theorem, previous axioms, previous definitions. So this is what we want to do for this part of our course, for this unit. So we're developing our understanding of geometry. So there's a lot of things that we know that we want to forget that we know them. So again, what we're going to do is we're going to do a proper axiomatic development of geometry. So we want to start with a blank slate. We want to start with nothing. So the definitions, what we start off with, we'll begin with the undefined terms. So from those we can create definitions using terms that we already have. And then when we write a proof, we can only use terms that we already know and have defined, axioms that we have assumed, and theorems that we have already proven. And at this time right now, that's not very much, right? Because we're forgetting everything else that we know. So what do we know? What do we want to use? What we do want to rely on is our knowledge of the properties of the real numbers. Of course, we don't want to forget how to have done algebra and how logical arguments work. Okay, these things are not about geometry. It's the geometry that we want to have an axiomatic development of. So we're going to use those things, right? Our knowledge of these things to help us develop geometry. All right. So I kind of skimmed over that previous page. I would encourage you to go through and read it yourself, spend a little bit more time on that. And if you have any questions, feel free to ask. But we want to start. Let's start our development. So we have two undefined terms, point and line. Although technically we do have a definition for line, right? A line is a set of points. So a line L is a set of points. And we should have an understanding of that. So first, the existence postulate. Our first axiom, there is more than one point. More than one point. And the set of all points is called the plane. Excellent. Much like we have notation for the real numbers, we can also denote the plane by P with double lines. All right, our first definition. A point is on a line L if and only if that is a point in the set of points called the line. Okay, so L is a set, so P is on the line if P is in the line. right? It's in the set of points. We can also say that L contains P. That would be the same thing. P is on a line L, L contains P. Same thing. So here is a line L. Remember, lines go on infinitely in both directions, and here's our point P on the line. Awesome. All right, the incidence postulate. If A and B are distinct points, okay, if A and B are two distinct points, A, B, then there exists a unique line containing A and B. Okay, and we can draw that line like this, and it is the line AB. Notice the arrows here, right? So the line goes on infinitely in each direction. We have arrowheads on the line above AB. So we have that 2 points always lie on a common line, but we don't necessarily have that any 3 points lie on the same line. When we do have this situation, we say that they are collinear. So 3 or more points are collinear if and only if they all lie on the same line. Excellent. The distance postulate then, our third axiom. So to each pair of points A and B, there corresponds a unique non-negative, right? Non-negative number called the distance between A and B. It is important that we remember that this is a non-negative number. The number is denoted by AB. Okay, we've seen some of these things before and we've talked about them. So this is just an emphasis that we're forgetting, right? We're forgetting pretty much everything from sections 1 through 7 and anything that we may have known outside of that as well. We're developing, so we're making some restatements here. We say A and B are equidistant from C if and only if the distance from A to C is the same as the distance from B to C. Excellent. Notice here, though, this only tells us that there is a distance between 2 points, but it does not tell us at all how to find the distance between 2 points. And if we consider different techniques or different flavors of obtaining distance between 2 points, then what we end up with are different geometries. So if we use the distance formula that we're familiar with, we would find that what we have is our usual Euclidean geometry. But if we define the distances a little bit differently, then we can end up with other geometries. We'll take a look at some of those other geometries later in this course, I believe in this unit or the next, in fact. All right. We'll take a pause there, or here rather, and we'll start the next video with a little bit more of a discussion on distance. So we'll pick up right where we left off.